All right, we've gotten all our data. Let's talk about what we're going to do with all these numbers from the titration data. First, probably goes without saying, but you have to take all your final readings minus initial burette readings to actually get the volumes used in all your titrations. In part A, we had volume of HCl and volume of NaOH for each of those trials. In part B, we only had a volume of NaOH for each of the trials because the other part, the tartaric acid, we kind of have a volume, but it's not the same kind of, we have really a mass that we weighed out. All right, so calculate those volumes from your burette readings. You're going to calculate the molarity of NaOH. We've talked about how to do that. I'll go through it again in part A. And then we're going to find standard deviation, percent relative standard deviation in part per thousand. We call it error, but it's really precision. Anyways, and by the way, you can use the Google Sheets functions to do those, which makes this a lot easier. All right, so once you have an average molarity of NaOH, now I'm going to use that with my part B data. So I'm going to take that and the volume of NaOH used to figure out the moles of NaOH used for each of the trials. I'm going to take that with the coefficient ratio to determine the moles of tartaric acid in each of those 3 titrations. And then when I'm considering the mass, I need to proportion the fact that we weighed out a whole gram, but then we didn't use all 1 gram of that because we dissolved it in 100 milliliters, but only took 20 milliliters of that. So I have to use proportioning to determine the mass that was in each trial. And then from my mass of moles of tartaric acid, mass divided by moles is molar mass, I can calculate an experimental molar mass. Get an average, get a standard deviation, get a percent relative standard deviation on that. I'll go and find the actual molar mass from the chemical formula of tartaric acid, which means once I have the actual number, I can calculate a percent relative error. And then we're going to go back and do some statistics on the whole set of class data for part A. And we'll find the average, the first quartile, the third quartile, the interquartile range, the outlier boundaries, and any outliers we have. All right, generically speaking, the task of titration is, I know something about the titrant, tell me something, some property about the analyte. So it's always going to be these same 3 steps. We know about the titrant, find how many moles we have of titrant. Almost always, if we're dealing with titration and burettes and it's a solution, it's going to be molarity times volume. So pretty much step 1 is molarity times volume of the thing that I know the molarity of. And then we're going to multiply that by the coefficient ratio of the reaction to figure out how many moles of the other thing I'm interested in, the analyte. So don't skip that step. A lot of times the coefficients are 1 and 1, and so it tends to be the same answer, but in a lot of cases they aren't. And you will get bitten again and again and again if you skip this step. So don't. So I know my moles of one thing, and then what are the moles of the other thing. And then once you have moles of the thing you're interested in, convert that to the property you're interested in. Maybe it's mass. I need to know its molar mass. Maybe it's molarity. I need to know the moles and the volume. Maybe it's pressure, volume, or temperature if it's a gas, so whatever it is. Again, this is the roadmap. So we start with what we know, get it to moles. Take the moles of what we know times the coefficient ratio, get it to moles of what we don't know. From the moles of what we don't know, now we can get it to the property of interest that we want for what we don't know. All right, so what equation are we using when we're trying to find that first step? Which one do I know? How do I know if I use molarity times volume or whether I use molar mass? It depends on what I'm dealing with. If the substance is a solution, in this lab, it's almost all solutions. So almost all of our labs, when we're looking for molarity, it's going to be, when we're looking for moles of titrant, it's going to be molarity times volume. However, in Gen Chem 1, you used a lot of pure solids, pure liquids, where it was just one substance. If you know what the one substance is, then you can use molar mass. Moles is mass divided by molar mass. So I can weigh it and use molar mass. I can't use that with solutions because there's more than one thing in there. So which molar mass do I use? The molar mass is only appropriate for part of it, so I can't. So use the molarity in those cases. If I did have a gas, I could use PV equals nRT rearranged before. And moles is equal to pressure times volume over R times T. We aren't going to be dealing with gases in this semester, just saying, so it's really going to be either molarity times volume or mass divided by molar mass. But I can only use molar mass if it's a pure sample. And almost all of what we're doing this semester is going to be solutions. All right, so how do I get part A data? Again, when I have my analyte, I want to know the molarity or I want to know its volume, which is commonly what we're doing. I'm looking for what is the concentration of this unknown thing. The 3 steps are, step 1, find the moles of what the thing I do know, the titrant, so that's going to be molarity times volume. Then I'm going to use a coefficient ratio in step 2 to figure out to the moles of the thing I'm interested in. And then if I want molarity, it's going to be those moles divided by liters of what that was. So in our case, let's step through an example. 50 milliliters of a solution put into a flask, a few drops of phenolphthalein. It's known to contain HCl, but we don't know its concentration. That means HCl is my analyte. That's the thing I'm trying to find. 28.39 milliliters of 2 molar NaOH added to the solution using a burette. It turns light pink color, so that's telling me we're at endpoint. What is the concentration of the original HCl solution? So again, the thing that I know is the NaOH, because the thing that I don't know is the HCl. So I start with finding moles of NaOH. By the way, in your part A, it's the opposite. HCl is the one we knew, and moles and molarity of NaOH is the one we don't know in our lab example. But in this example, the thing I don't know is the HCl. So I begin with NaOH. So I take its molarity, multiply by its volume in liters to get its moles. And then step 2, use the coefficient ratio. You have to have the balanced chemical reaction. Don't skip that. For NaOH and HCl, it's 1 and 1. So I'm multiplying by 1, dividing by 1. I get the same answer. And tartaric acid, it's a diprotic acid. It's not going to be 1 and 1. So make sure you're using the coefficients. All right, part 3 is now, I want the molarity of HCl, but I know how many moles I have. I know how many liters I have. So it's 0.05678 moles, because I figured that out from the moles of NaOH. And I know the volume from the original lab data, and I can calculate it. It's behind there. It's like 1.13 or something like that. Okay. Let's talk about a little bit of a faster way to do this if this is the task I want. Again, if my task is I know molarity and volume of one thing and I want the molarity of another, I can take those 3 steps. Here's my step 1. Here's my step 2. I'm going to feed this answer into this formula for step 2. I'm going to feed all of this onto the top for this formula of step 3. And I come out with this one step. After I rearrange this formula, I come up with the coefficient of the titrant times the molarity of the analyte times the liters of the analyte equals the coefficient of the analyte times the molarity of the titrant times the liters of the titrant. Or CBMAVA equals say CAMBVB. So this has coefficients in it. It looks like the dilution formula, but it has coefficients coming in it. So this one can be used for titration. Just make sure you're being very consistent about what is A and what is B. It doesn't particularly matter what you label A and B, be consistent. A lot of times we use A for the acid and B for the base. So doing that same problem, but with the one-step formula. In this case, my coefficient of acid and coefficient of base from the balanced reaction of NaOH and HCl are both 1. So my Ca, Cb are 1. And I have 50 milliliters of solution, and that's the one containing HCl, so that's going to be my Va. And then I have 28.39 milliliters and 2.0 molar of NaOH, so those are for the base, so those will be my Bs. They go here. I rearrange it, solve for it, get the same answer, 1.136. So this is option. And it works for the part A. It won't work for part B because I'm not trying to find molarity in part B. I'm trying to find molar mass. So let's talk about part B data. All right, first, this screws everybody up. I weighed out a sample, but then I didn't use all of that sample that I weighed out in each titration. I only used part of it. Remember, we weighed out 1 gram of tartaric acid into 100 milliliters, and then we diluted it to 100 milliliters of solution. But I didn't take all 100 milliliters of that solution and titrate it. I pipetted out just 25 milliliters of it. So I took 25 1/100ths of it. In other words, it's the ratio of the volume you pipetted into the titration flask divided by the volume of the solution you prepared from that mass. So the ratio of the volumes, in our case, it's 25 and 100. But it could change, it could be different. Anytime you use this technique, you would take the ratio of the volumes and multiply that by your mass to get the mass used in just one sample. So we're going to have to multiply our mass dissolved by 25 or 100, which is 1/4, to get the mass of just one titration. So let's go back. Again, we need molar mass as grams per moles. I can get the grams from that, what we just talked about. I'll take the mass that I took and multiply it by the volume ratio to get the mass that was in one titration. But I need to get this moles of analyte, in our case, moles of tartaric acid. Start with the thing I know. In part B, I know the molarity of NaOH because I found it in part A. So I'm going to use the average molarity from part A as my molarity of NaOH. Multiply it by the volume of NaOH you took from the burette readings, and that's my moles of NaOH. Don't forget to use this in liters. Don't use milliliters, use liters, and I'll get my moles of NaOH. Now I have to multiply by my coefficient ratio, though. In this case, my analyte is the tartaric acid, and the titrant is NaOH. The tartaric acid is a diprotic acid. There's 2 hydrogens. It needs 2 hydroxides, so it means it needs 2 NaOHs. If you write out the balanced reaction of tartaric acid with NaOH, we find out that the analyte or tartaric acid has a coefficient of 1, and the titrant or the NaOH has a coefficient of 2. So I have to multiply my moles of NaOH by 1/2 to get moles of tartaric acid. Don't skip that step. And then that's what goes on the bottom. Molar mass is grams that I figured out from my proportion that I took of the volume and of the mass. And then the moles of analyte is from step 2. I calculate my molar mass. I'll do that 3 times and get 3 different molar masses for my 3 trials. Let's go back and remind ourselves about standard deviation. I'm putting the formula up not because you need to use the formula anymore. You use this formula for the entire Gen Chem 1 lab. I know you got really good at the math. And the reason why I wanted you to learn how to do the math from the individual steps is that I'm seeing what is the difference between my trial and the average? What is the difference between my next trial and the average? So how far away is it? How far away is this one? And I'm squaring it. Then I'm adding them all up, dividing by, so I'm kind of like taking an average of it, and then I'm unsquaring it with the square root. So it's kind of like an average deviation. That's what standard deviation is. It's like an average deviation from my average. And so in this case, my average was 5.75. I end up with a standard deviation of 1.71. Now, go ahead and use the Google Sheets function standard deviation to calculate this. You don't need to calculate it by hand anymore. So equal standard deviation dot S for the sample, and then in parentheses you're going to list off the sample, the data that you wanted to take the standard deviation with, all your trial molarities or molar masses, and you can calculate the standard deviation. Don't forget that the standard deviation is a percent relative standard deviation. So percent relative standard deviation is where I take my standard deviation and I divide it by the average. It's like, how big is this standard deviation compared to the size of my number? In other words, if I was off by $1, I'd say, well, was that good or bad? I counted up a set of money and I was off by $1. Well, if the sample included had $5 and I'm off by $1, I did a pretty junky job. I mean, that's kind of far off. But if it was $100,000 and I was only off by $1, I did pretty good. So the percent relative standard deviation tells me how big is my standard deviation compared to the size of my number. And that's going to tell me about precision. How close are my values to each other? That's a precision thing. Accuracy deals with how close are things to the actual correct answer. I don't know the correct answer for part A. I can't do a relative error. I do know the correct answer for part B because I know the molar mass of tartaric acid. And remember, for the percent relative error, it's what was my experimental value, what is the real value, subtract them, divide by the real value, multiply by 100, and it's like, how close were you to the correct answer? So precision is how close were they to each other. That's standard deviation, relative standard deviation. Error is how close were they to the correct answer. I have to know the correct answer to do it, but if I do know it, that's going to actually give me accuracy. How accurate I am is how close I am to the actual answer. So in the questions, I'm going to ask you about accuracy and precision. These are the numbers you should use to answer those questions about the sample I give you and then about your own data. Another thing we can do is part per thousand relative error. It's really, okay, I say error. In our case, we're going to use the average as our accepted value, so it's really not an error. It's more like a part per thousand deviation. So this is how close are my numbers to each other. In our case, the way we're going to calculate part per thousand is going to be a precision measurement. So, and again, it's similar, but it's out of 1,000. I take the difference between two values. In our case, we're going to use the average as the accepted. The average is not the correct answer, it's just the average. So we're really doing how close are they to each other, which means we're going to be doing precision. So what is the average molarity, in this case, part A, the average NaOH molarity, minus the trial molarity. And then I multiply that by 1,000 rather than 100 like we normally do. And I'm dividing it by the average value. So this is, like I said, this is kind of like a relative standard deviation. In titration, I'm trying to get some very accurate answers. And so for accurate and precise values, right, we're using 4 sig figs and we're using burettes that have 2 decimal places. We're using volumetric pipettes and volumetric flasks. We're really trying to do a very precise job. Therefore, good precision when we're doing titration is 5 parts per thousand. So they should be within 5 parts per thousand of each other. So we're going to calculate this for each of our trials. So again, we're going to use the average molarity of the 4 trials or the 3 trials, and then we'll use each trial one to figure out what those are. If you have one, so they should be all under 5. Maybe they're not, maybe they're at least all under 10 parts per thousand. If one is much larger than all the others, so I have like 3 and 7 and 26, the 26 is like, that's much farther away from the other 2. That may be suggestive that it's an outlier, but with only 3 things, I can't say. I need statistically relevant information to tell me that it's an outlier. And I can't do statistics with a sample size of 3. It's just too few. In order to do statistics, I'm going to need like a sample size of like 12 or 20 or 30. So I can't really do this, but at least it's suggesting, hey, maybe that one is wrong. If they're all large, it suggests like I can't get close. Like I just have darts all over the dartboard and I'm not close. I don't know which one is good. That's suggesting we really need to clean up our technique, as opposed to one thing went wrong on one trial. It's saying in general there's not a very consistent task of what we're doing. The value of what we're looking for, again, this changes per task. Okay, so class statistics. I do want you to get this idea of outlier analysis. In research, sometimes a value just seems off. I did something a bunch of times and one of them is way off, and I'm like, I can't believe that I'm not going to be able to publish my results because one value is bad. And yet I can't say, I don't like that one, I'm just not going to include it. It looks far away, I'll just ignore it. That's fraud, right? If I've calculated, so you're like, okay, well wait, but if one is way off from the others, probably something went wrong. So the only way I can reject it without it being fraud, and I'm simply massaging my data and choosing what to use and what not to use, is to use statistical evidence to say, this one is so far away from the other ones that I don't know what went wrong, but something went wrong. I can reject that trial and not include it with my data, and I can say all my other data is good. And so I want you to see how we go about doing this, because this is an important task that we have when we try to publish results. All right, again, I have to have a large sample of things. In our case, as a class, we have a large number of trials. Each group did 3 titrations of that NaOH, and we all use the same solution. And we have 12 groups times 3, that's 36 values. So we have a large number of values that we can now do statistics on and see, are any of those trials outliers? All right, so first you need to use your volumes of HCl and NaOH from each trial and calculate. We also know the molarity of the HCl. That's enough to calculate the molarity of the NaOH. Basically, this is exactly what we did in part A, but I want you to get it into like a little quick formula so that you can use Google Sheets, calculate it for the first value, copy it to all the others. Okay, now we're going to sort the list from lowest to highest. And I want to find the value that's a quarter through the list and a value that's 3/4 through the list. We're going to call those first quartile and third quartile. I'm going to subtract those 2 values to get the interquartile range. It's like a range of like where half of my data lies. And then I'm going to determine my outlier boundaries as being 1.5 times where 50% of the data lies, past the high and the low. And we'll see if there are any values that are outside of those boundaries. If they're outside those boundaries, I have statistical justification to say there's something wrong with that trial. I'm going to reject it and exclude it from the average. All right, so again, definition. First quartile is the value that's 1/4 along the way of a set of measurements when they're in a sorted form from lowest to highest. And Q3 or third quartile is the value that's 3/4 the way along the list in a sorted set of range. And then the interquartile range is the third quartile minus the first quartile. So it's like 1/4 of the data. If we go to half data would be second quartile. It's also the median. And the third quartile. If I subtract third quartile, first quartile, that's like where half of my samples are between those 2 values. And that gives me, where a lot of my stuff is. Outliers then, again, we're saying they're far, far away. So one accepted method is to define far, far away as 1.5 times past of the interquartile range outside of the third and the first quartile. So my lower boundary is the first quartile minus 1.5 times the interquartile range. And my upper boundary, it says like if it's past this, it's really far away, is the third quartile plus 1.5 times the interquartile range. All right, so as an example, if I had 11 trials and I had already calculated the molarity for them and I sorted them from lowest to highest. So the first one, I'm just putting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 so I can easily find where I am in the list. I like to assign an index. All right, so this is my lowest value, this is my highest value. Since there's 11 items, I want to find the first quartile. That's 1/4 of the way through 11. Well, 11 times 1/4 is 2.75. Since it's not a whole number, I have to choose what to do. And there's a variety of ways I can do it. I can take the average of the second and the third in values. I could take the closer value. I could interpolate it, but we're going to take the closer value. So closest to 2.75 is 3, so we're going to take the third value, and that's 0.4552. That's going to be my third quartile, or first quartile value. And then my third quartile is 3/4 the way. 3/4 the way through 11 items is 8.25, so the closest one will be the 8. All right, so here's my 8 is 0.4571. So I have my first quartile, I have my third quartile. My interquartile range, I'm going to subtract 0.4571 minus 0.4552, that's 0.0019. So my lower boundary is defined as the first quartile minus 1.5 times that IQR. So it's going to be my first quartile, 0.4552, minus 1.5 times this range difference. That's going to be way down here. And that turns out to be 0.4524. My upper boundary is the third quartile plus 1.5 times RQR, which is 0.4600. And again, remember, sometimes you can mess up and screw up which one you do the minus and which one you do the plus. It's important that your lower boundary is the lowest possible number, lower than your first or your third quartiles, and the highest the upper boundary should be higher than all of your quartiles. So double check that you got that right. All right, so now I'm looking for any values that are lower than 0.4524. And 4537 is above it, but 4496 is below it. So that means index number 1 is 0.4496. That's an outlier because it's lower than the lower boundary. Similarly, on the high end, are there any values above 0.46? Well, the last one is 0.47, so it's above 0.46. It is also an outlier. So in this case, I had 2 outliers. I could remove index 1 and index 11 and average those other 9 answers and get that as a better average than including them. I can exclude them from the average. All right, so in this particular case, we had 1 lower outlier and 1 upper outlier, but there's no rules. I could have no outliers. I could have 3 outliers on the low side and none on the high side, or none on the low side and 2 on the high side. It's whatever it is. It's just saying I can only exclude things that are past those outliers. So you're going to do that with your data, decide how many of the trials actually were no good and which ones we can exclude, and you'll come up with an adjusted class average for the NaOH and determine how close yours was to that adjusted average. Get an error value on that. And then you're going to do some questions about precision and accuracy, which go back into that statistics slide that I talked about. All right, enjoy writing up your lab.